way. Nope, not many people from Australia then. I'll try and speak a bit slow because people have said they've got some problems with my accent, so we'll see how that goes. If I'm talking too fast or that, if you could let me know, it would be appreciated, and I'll try and slow down so people can understand. This talk will cover various methods of making binaries harder to analyse and break and just do things like that. Additionally, we'll cover various methods of watermarking the binaries. Accompanied with this presentation is a relatively in-depth paper on implementing these things on the Linux operating system. Additionally, the talk notes and slides will be available on the the Feline Menace papers section. In the interest of having this presentation applicable and useful for everybody, I've decided to keep it at a moderate technical level so that people can best get the information from it. I've tried to cover some basics where applicable, but it's a bit hard to strike a balance between the two. Finally, if you have any questions throughout the presentation, I prefer to keep it at the end because there's a fair amount of material and I'd like to get through as much as possible before I run out of time. Defence in depth is a term borrowed from the military and is used to describe measures which reinforce each other and hide the defender's activities from being observed. Defence in depth usually starts off by defining the problems you're facing and obtaining a clear picture about how potential methods and ideas to protect what you're trying to protect from. Sorry, we'll try that one again. Defence in depth usually starts off by defining the problems and the significance that they have, and then rating them. Once a clear picture has been obtained of what you're trying to defend against, you can then evaluate potential methods and ideas and go through the process. It's pretty important to clearly define what problems you're trying to solve. It's pretty easy to go off and lose track of what you're trying to solve and thus waste a fair amount of time. As time goes by, people probably will find problems with how you're... So it's been a long time since I've done a presentation in public before, and I'm doing a lot of ums and ahs, I'm conscious of this. As time goes by, you'll need to re-evaluate what you've done and see what other people have done to break your systems. By analysing your plans from an attacker's point of view, you'll be able to identify what you would have proposed to do as being weak and not worthwhile to implement due to time constraints. In general, if you can ask yourself what you can do to make your system more robust and have the attackers less chance of doing what their goals are successfully, you'll end up with a general system that's better. During the attack analysis, you'll probably think of additional methods that will help your efforts in thwarting an attacker. These should be carefully evaluated and analysed to see if they will be effective and if they are feasible to implement. If you haven't analysed things from an attacker's point of view before, it can be quite hard to do. You have to learn what the attackers are capable of and I'm just going to read off this. Sorry, I'm not doing a very good job of memorising everything, and I apologise for this. One aspect that people seem to sprout off as being a good idea is to somehow damage one's computer if they detect software that can be used to analyse a program's operation. Such an example of such a program is Soft Ice. While the motivation of this aspect of this can be seen from the developer's eyes, there are many cases where people legitimately have such software in the machine. For example, developers or security analysts. As there are tools out there to hide various debuggers from being seen by applications, it usually isn't that much of an added protection. Therefore, you'll run the risk of annoying legitimate customers of your software. In addition to that, in many countries it is illegal to deliberately damage their computer systems. Given these points, it would be a bad idea to do anything that would break various laws in the countries where your software is sold. A better and more constructive use of your time would be to work out various ways of misleading and slowing down potential attackers on your software. For example, if you detect a debugger actively debugging your binary, you could change various algorithms so it results in incorrect executions and invalid values being used. If you separate cause and effect of where you're doing these detections and where the problems actually happen, it causes a lot more effort to be spent on the attacker's time trying to work out where these things happened. By utilising various techniques to inhibit an attacker, you'll increase the amount of time, motivation and skill needed to break the protection schemes around the binary, and thus provide more time until eventually the attacker's goal is reached. To summarise the slide in general, and I apologise about this slide because I had actually meant to do some graphics for it, but at the last minute it turned out that I really suck at drawing graphics. So there was actually meant to be pictures there, so I apologise for that. But to summarise the slide in general, a majority of protection schemes generally implement various layer defences in a sense that you can attack and remove layers generally without impacting the operation of the protected binary. If a protection scheme is going to be robust against analysis and attack, it needs to have it so that attacks on the program over the protection overall reach into the core stability, usability and functionality of the program. I'd like to finish off this section off with a quote from Nietzsche. He who fights monsters should look to it that he himself does not become a monster. And when you gaze long into an abyssus, the abyss gazes into you. The relevance of this is left up to the people present to determine. Watermarking can be used in many situations, such as tracking or identifying whose copy of the software was released to various WERS groups, for example, by letting your users know that you have the capability to identify who released software, you deterred them from doing so. Of course, this method isn't applicable when you don't have like individual sales to customers. Whereas if you're like doing press CDs, it's harder to watermark, well, it's impossible to watermark the binary without doing an individual press CD per person. And even then you usually don't have the customer's details to make it worthwhile. Apart from the deterrence factor, another benefit of watermarking is obvious if you have the ability to either prosecute people responsible or the ability to tarnish the reputation of the company who is responsible. Unfortunately, watermarking doesn't prevent against general fraud to obtain the software. In general, a fragile watermark is used for authentication and integrity attestation, and it is used to guarantee an item, for example, a document that came from the right place. An attack on this type of watermark would be to modify the item without breaking the watermark. On the other hand, we have robust watermarks. Robust watermarks are generally used for copyright purposes and or authenticating who originally inserted the watermark. An attack on a robust watermark would be to modify the item in some way that to render the watermark ineffective or to remove the watermark's presence completely. Watermarks generally also have another property which indicates if the watermark is visible or invisible. Visible watermarks are meant to be publicly recognised and can be human perceivable. Invisible watermarks, on the other hand, are meant to be recognisable only to authorised people, and thus it makes it harder to know where to attack to break the watermark. Depending on how much effort you wish to put into designing the watermarking system and how it is to be used, there are various methods that can be used to insert the watermark. The most simple one to implement is just have a simple incrementing counter for each customer. This system is obviously weak if an attacker has multiple copies of the software, because they can then do binary analysis, find out where it's different. When an attacker, other areas that can be used for storing the watermark can be the order of certain operations, and often cite an example of how various initial values for a function are loaded. For example, two variables can be initialized in two different orders. This method is also vulnerable to the attack described above. The best method is to work around this is to make each binary as different as possible. For example, the compiler flags, such as optimization flags, can be changed. The order of which object files are read in can be modified. The layout of structures can be randomized per compile for each customer. In turn, the transformation of the binary by the randomization can also be used to identify whose copy it is. There's been some research into the feasibility of making software watermarks tamper-proof, so it becomes a lot more difficult without impacting the operation of the program. There's a research paper I read about this, and I don't have its name on hand. I've actually got a big XXX for me to fill in, so I don't know the name of the paper I read at the moment, but I'll fix it up when I do my slides and publish them. In general, to summarise a research paper, they make a graph and pass it during runtime to obtain data constants used in the program and use the obtained values in operations, such as addition or printing a string. Because the data returns are also used for passing the graph in theory, if you change the value, the correctness of the program is in jeopardy in other parts of the code. An interesting part of this document, though, that they noted that they didn't do any field testing of their research to find out how robust this implementation would be. Obfuscation is the act of deliberately making something harder to analyse and understand. The aim of obfuscation is to increase the time, skill and cost required to analyse protected code. Obfuscation can be applied at both the source code level and assembly level. The probably most famous obfuscated source code would be that from the International Obfuscated C Code Contest, also known as the IECCC, which is an annual competition that's been running since 1985, and is where people can submit their obfuscated code to be judged. Some of their code has been like CRC in big letters and actually being a CRC implementation. Sorry about that. While obfuscated source code may be useful for some purposes, it is not the end product that is shipped to the customer, and thus generally isn't the best place to focus your efforts. Some people have previously tried to obfuscate programs by having large amounts of junk code, which doesn't really help for obvious reasons. Some viruses, for example, have used techniques as redundant prefixes on instructions that doesn't make sense. For example, repeat while not zero on a subtraction instruction. It's also used some opaque conditionals to trick control flow analysis and make it harder to automatically map out the program's operations. It's used some alias opcodes. For example, move EAX, EBX can be encoded two ways. While these measures were semi-effective, the mechanisms were being used as a wrap around the true virus code. Since a true virus code could be reached, it could be analysed and taken apart. Implementing a serious obfuscation engine is a lot more involved and has various aspects and things to consider. Code layout obfuscation covers the area of changing the layout of the code. For example, it might be splitting a function into small blocks and spreading them all over the binary, changing the variable lifetimes or variable orderings. Data obfuscation makes it harder to find references to data and make it harder to analyse. For example, it could be converting static data into a function where the string is generated, inserting more references to data to make it harder to locate where a certain object is being looked at and analysed by. Control obfuscation covers inserting opaque conditionals, making logic choices harder to determine by static analysis, duplicating blocks of code independently obfuscating each block. Some of these changes could include flattening the control flow so that it is not irreducible. Preemptive obfuscation covers making Preventive obfuscation covers inserting specific obfuscation constructs to target a particular problem. Some things that are worth targeting is how hard it is for a human to automatically analyse the program and how hard it is to automatically unobfuscate a binary. As determined by Christian Goldberg, Clark Tomberson and Douglas Lowe in their paper entitled A Taxonomy of Obfuscating Transformations, obfuscation is classified by its potency, resiliency and cost. For more information and in-depth discussion on this, see the mentioned paper. The term potency refers to how much time and effort and skill is required by a human to understand then remove the obfuscation construct. Various methods may dramatically increase the potency of the algorithm, but may not necessarily reflect upon the other targets. The term resiliency refers to how much time and effort and skill an attacker needs to write a program to automatically unobfuscate the construct, and how much resources the unobfuscator requires to run. Increasing the resiliency will help prevent automated unobfuscators. The term cost refers to the impact of implementing the previous two methods on the execution of the program. For example, a method that causes huge memory usage or a long execution time would be said to have a large cost. By using these metrics, it is possible to objectively rate the usefulness for particular constructs and decide if it is useful to include them and where to include them. Opaque constructs are code blocks which always result in the same control flow. The general aim of an opaque construct is to be difficult to identify and remove, thus increasing the resilience of the affected code. Opaque constructs can be inserted and used in logic decisions and data decisions. The term instruction context refers to analysing a block of code and determining if the instructions depend on certain orders of execution, what ways the registers are used, and determining the lifetime of the registers. Once this information has been gathered, it is possible to rewrite the instruction context. Some things that might be done are to modify which registers are being used for the particular code blocks, what arguments are being passed to instructions, and inserting irrelevant instructions. By sampling the instructions in the program you are obfuscating, you can make it so that the instructions you're inserting are similar to the ones that already exist and are in the same frequency range as previously. This will help hide where the inserted instructions were placed. In order to make automated analysis of the inserted instructions, serious thought should be given to make it so the inserted instructions perform reads and writes to memory after operating on registers. This makes the program, the inserted code, look a lot more like a standard operation of the program and not just because if you don't do that, you can find out where the registers are being used, and then if they're dead, like dead code where you get written to one register then written to again, you can remove where it did the first one, for example. Automated analysis of the control flow loops can be made harder by inserting new constraints inside loops. The aim here is to break standard compiler-generated loops so it is harder to automatically identify and recover them. This could be achieved by inserting an opaque construct which always ends up adding 0 to a value which is used in a conditional check, inserting spurious instructions between initializing values and adding extra comparisons which have no effect. Data obfuscation is where you obscure the data used in the program and make it harder to find where various pieces of data are initiated and used. By converting static data into pieces of code, you can make it so that it's harder to analyse and modify, as people need to first locate where the data is being initialised and what constraints are being placed upon it. The references to static data can be easily obtained in the object files during compilation time, as there will be relocation entries which will patch up the binary during the linking stage. This allows us to easily convert pieces of data into functions without worrying about following execution flow and finding all references to the static pieces of data. By modifying the Okay, sorry about that. I haven't been updating the slides that I've been talking about. By modifying the vtable in C++ classes, the function inside a class can be rearranged and new junk functions can be added or inserted into the class. If the class is said to have its vtable rearranged, the obfuscating code would have to track through all the appropriate code and modify them so that they point to the correct entry inside the vtable. As well as modifying a class's vtable, you could modify structure layouts and add extra items of various types and perform dummy operations on it. This increases the time involved with reconstructing what a specific structure is used for, what its members are, and how they are referenced. In order to increase the time needed to analyse structure usage, you could implement a simple linked list inside the structure or a doubly linked list that gets modified over time. This will make people spend more time analysing the program, finding out what it's doing and if it's useful. In order to increase analysis time of binaries, certain data types, such as an integer, could be converted into a class. The class would be then responsible for performing various operations on the variable, such as addition and subtraction. Additionally to that, it would be made to appear that the class is also doing a lot more. Code can be split into basic blocks by identifying the blocks of instructions that don't rely on previous instructions to perform their operations. Once a chunk of code that is to be obfuscated has been broken down into basic blocks, they can be operated on. Once you have some instructions inside a basic block that don't rely on each other, the instructions could be swapped around to make it slightly harder for humans to analyse. Additionally, after the basic blocks have been gathered, you can independently obfuscate them. Some of the operations you might add to the blocks are reversible operations to the basic blocks, such as adding or subtracting a number to a register or changing which register is being used for the operations. These modifications will have to be reversible so that if a basic block that has other code references to it, for example inside a loop, the changes need to be able to converge so the program will be able to continue executing fine. Code flow reduction is where you remove where you modify the code flow conditionals to be as flat as possible, thus removing a fair amount of information available about a program's behaviour, and depending on implementation, a fair bit harder to recover that information. The control flow reduction could be achieved by implementing a simple switch table and setting up the switch table inside the code, or other such methods such as calculating the address to jump to and jumping to it from a central point. The more resistance there is to static and runtime analysis, the better the method is, and the harder it will be for people to recover the code flow. In general, you'll want to reserve obfuscation for important functions, as it will have an adverse performance impact. If you're implementing the obfuscation stuff yourself, it will also impact upon delivery times if you've got other projects happening. A decent licensing implementation will take a fair amount of effort to implement so that it is stable, reliable, and provides a decent amount of security against determined attackers. Ideally, you'd like the licensing scheme to be robust even after they've paid for the software. It seems obvious, but if you don't want people to have some parts of your code or data in the demo versions, don't include it in the demo version. If the license scheme is based upon people entering a license code, you could generate a decryption key from the license data. However, depending on how you implement it, you may accidentally make it so that the protected data or code can be trivially recovered. In order to improve the robustness of the licensing code should directly relate to the correct operation of the program, and thus cause incorrect operations when should an invalid license code to be entered. One method of doing this is to utilise the license code in logic and data choices in your code. With logic choices, you would have two versions of like a particular function, but one would be slightly buggy. With data choices, you could use it to set flags correctly for functions. You have to make it hard to identify where the checks are coming from by making it hard to follow the data from where, once you've entered the data, into where it's being used from. The aim behind that is to make it extremely hard to follow all the logic choices in the application and to follow all the data paths as well. This will result in people having to spend significant time analysing the code and data flow trying to determine if it's relevant. If the license code is based upon people entering a string, you can make life a little bit easier for them by including a 1 or 2 byte checksum. This allows you to inform the user if they've entered an incorrect license code without giving anything away about the validity of the license code or how it was generated. This also has provides a slight detour for an attacker, as they may see the checksum, compare and think they need to patch that location, or alternatively, they'll try to write a license key generator. By using license code information without checking for its correctness, you are avoiding giving away potentially critical hints to an attacker, which means they have to spend more time analysing the code to see what it is doing. After sketching out your license scheme and how it operates and what it will affect, think about ways you can break the system. Depending on what you're aiming for, you may want to improve upon what you've already outlined above and find other methods, or alternatively find other methods of improving the robustness of it. Okay, and I've done it again. Sorry about this. Virtual machines are self-contained emulated machines which have their own assembly language and memory areas. They can be extremely simple or extremely complex. Such a complex one would be Java, although the Java implementation has a lot to be designed with how hard it is to analyse. Virtual machines can be completely bytecode driven, or they can use a just-in-time compiler to generate code that is executable on the native CPU that the virtual machine is running on. Since virtual machine instructions and implementations can be whatever the creator dreams up, they usually involve a fair amount of analysis to determine what opcodes are available and what they can do. They then have to get familiar with how the code is implemented inside the virtual machine, how it is put together, and what constructs are used, which makes it harder and more time-consuming to analyse. The general disadvantage with virtual machines is that they take a fair amount of effort to design and implement, and then to write code that is executed in them. Additionally, they only need to be analysed and understood once before they lose their usefulness. This can be offset, however, because it's possible to randomise how the byte sequence is decoded, what the bytes map to, and how parameters to the opcode is accessed. This allows for a little bit of leeway which can be randomised for each customer or for each installation. Additionally, some other measures can be taken. For example, the byte sequence to be decoded can also configure various parameters of the virtual machine. The general idea behind modification of the executable file headers is to cause the program analysing the file to misbehave in some way, such as crashing the program or system and/or generating incorrect output from what would be expected of the program being used, and also to make the process more painful for people. Some techniques involve stripping the section tables or munging the symbol table from ELF files, inserting incorrect program headers which the analysis tools pass, or specifying invalid sizes which cause various tools to loop for a while and allocate large amounts of space, or alternatively cause a integer overflow. For ELF, a lot of tools use the section tables, and thus it is more useful to make the section table completely misleading. A method of this is to append another binary to your executable, and pointing the section header to point to the appended binary section table, and fixing up the file offsets so they all now point to the other binary. Because LineTool will pass the program headers, it will cause different memory layouts to be seen from the program's point of view and the operating system point of view. New methods can be developed by analysing how the operating system and associated tools load the binary and comparing with how the analysis tools pass the binary and using the differences to attack the tools. However, this is a standard arms race. Once you use these methods or develop new methods, people will identify the cause of the problem and will come up with fixes, even if it involves hand patching the vulnerable binary. Okay, I got that one right this time. There are a couple of various disadvantages with this, which may merit concern. For example, there is a portability between operating systems and various emulators, such as Wine. Most people tend to expect they can use their programs across different releases of operating systems, and some people will be able to like to run their software on other operating systems under emulators such as Wine. Additionally, occasionally you may like to debug your own softwares when you can't reconstruct the errors without the modifications to the binary. Additionally, some modifications to binaries will trigger antivirus softwares which will make your customers be more suspicious of what your software is and if it's affected in any way. In order to effectively slow down and deter attackers from breaking what you've done, the best method is to utilise multiple layers that interlock and that aim to protect each other from being analysed. The more robust the implementation is, the longer it will last. As mentioned previously under the licensing scheme, you shouldn't check for consistency or correctness inside the licensing code and just use them straight away. This will avoid giving away hints to people. You'll have to learn to attack your own implementation in order to identify weaknesses and keep one up from what other people are doing. Also, realising when and where to focus your efforts on what parts you're implementing will also go far because you'll be able to better focus yourself. However, to summarise in the end, if people are significantly determined, nothing is unbreakable given today's open hardware. While there is trusted computing in the horizon, time will tell if it's sufficient for the needs that people want. Okay. Any questions?
How does adding the online component, for example, the OpenGriffiths format, with download keys from a central server, how does that change the analysis of cost benefit? If you've got guarantees, for example, that people will be online recording the software, so you can sequester information not on your machine, but on your server.
You mean running code on the server side that people can't get to?
Right.
Yep. That changes things a lot because if they don't have the code that they're trying to use, it'll make things a lot better. It depends how people have implemented though, of course. It's certainly something to look that people can do, and it's certainly becoming a trend in the future. At the moment, that's not so much of a problem at the moment, though. Any other questions? Okay, I'll give it a wrap then. Not sure how much time I've spent.